All right. So anyway, a couple news articles, and all right. So people are talking about a pandemic, but they say this thing is not a pandemic yet, but it caused the stock market to fall by 1,000 points, and they have hundreds of cases in South Korea. Apparently, a pandemic is something that is spreading worldwide with no containment, and we aren't quite there yet, although it certainly looks like we're headed there. So this is something a lot of people are wondering about. If you find a GPS tracking device on your car, you can remove it, and that is not theft. The cops were tracking a meth dealer. They put a GPS tracker. He found the GPS tracker and took it off his car. So then they took that as an act of theft to get a search warrant to search his house and found the meth. And they said, wait a minute now, taking an unmarked thing off your car that you didn't put there is not theft. And that sounds about right. I know there's a similar issue a lot of people have brought up, that if somebody flies a drone over your house, can you just shoot it down with a shotgun? And it's a very similar issue here. I mean, do you have the right to do that or not? And the drone thing, I don't think has gone to court, but this has finally gone to court. And this one does seem to match common sense, I would think. But anybody putting any unauthorized thing on your car, you have the right to remove it. Anyway, so Bruce Schneier, a famous cryptographer, has joined this team from Tim Berners-Lee. These are big names. They're planning to make some kind of online vault where you put all your personal data and then you choose who gets to access it, their idea. I don't know how they're going to enforce this, but it is an interesting idea anyway. The idea being you can do something about everybody tracking you, because right now Facebook and Google and Pizza Hut and everybody just record everything about you and there's no control at all. So this is an idea to somehow limit that. This one company is getting upset about the fact that when you copy something to the clipboard, every other app can see it. Now, I thought this was exactly the way it should work. For example, you might have a password manager. You want to copy the password into the clipboard, and then you want to be able to paste it into any other app. So they told Apple, and Apple said, so what? That's fine. But some people are trying to see this as a vulnerability, and we'll see what happens. But certainly, my first reaction is to agree with Apple and say that is what clipboards are for. When you put something in the clipboard, obviously you're trying to move it to another app. So you shouldn't expect it to be concealed from other apps. This one caught my attention. Mismanagement device identities is costing a lot of money, and I didn't understand what they were talking about until I got down to the details. And let me see if I can somehow get this to fit on my screen so I can see things. There we are. Down here, they get down to the point. They're talking about SSH keys, and there was a nice paragraph down here, which I may not be able to find again, where, they worked with an airline. What happens is all the engineers use SSH keys, and they don't give them to the security team, and the security team doesn't secure them. So they found an airline company with 4 million SSH keys, and they have no idea who has those keys or who's logging in where, and they can't keep track of who they are or anything like that, which is what you would think. That's quite a mess. And from what I hear, this is very common with development environments. There are many different authentication techniques in use, and they're not actually being monitored and logged like they need to be. This is why I'm more and more in favor of compliance. Achieving compliance would require actually organizing your activities so you know who is doing what and you're keeping a record of that. And that is difficult to do and a big step forward. Anyway, Microsoft has now released, after 2 years of development, Azure Sphere, which is a Linux-based microcontroller service. Somehow this is using a Microsoft-developed version of Linux, and it is a hardware and software service that is supposed to secure Internet of Things devices. So I don't really understand exactly what it is from this, but I guess we'll be hearing a lot more about it. You're going to buy Microsoft-certified microcontrollers and use them, and they'll somehow be controlled by the Microsoft cloud, and their hope is it will make you more secure. It'll be interesting to see how popular this is. Microsoft has a very long track record of announcing things which everyone ignores and they just fizzle out. So we'll see if this actually catches on and becomes popular. It certainly is true that most Internet of Things devices are fantastically insecure and they're not managed by anybody, and having them somehow organized and controlled by some kind of cloud service might be better. Here's one of these stalkerware apps. These things are getting a lot of press from some privacy officials. This thing is called Kids Guard, and here's how they monitor it. And they advertise these things so you can catch your cheating spouse and stuff. So you put this on your phone, and now you see everything they do, every SMS, their GPS location, and everything else, which sounds really creepy, even to do to your own kids. And in addition to this being a questionable ethical decision to do this to people, they're also just dumping it all on an unprotected cloud server, which was, I think, an Alibaba cloud server. So they told them about that and they took it down, but this is extremely common. Not only do they spy on everyone, but then they just throw it up publicly in like an open Mongo database or something. This one is good for the pen testers. They found 6 critical PayPal vulnerabilities, and PayPal just refused to fix it, told them to get lost. They kicked them off the bug bounty program and everything else instead of dealing with it. So this is what most people trying to get bug bounties tell me. I hear a lot of this. It's bug bounty programs are not as wonderful as you might imagine, not at all. Anyway, tonight we're going to start a long chapter that's going to be 3 days. So I'm going to start this security engineering chapter, and then we're going to have student presentations. I've got 4 or 5 students that are ready. So that's it for today. So let's start with this stuff, which is here, security engineering. And I edited it today, but I only made very minor changes. So the slides I stuck online, I don't think they need to be updated. Anyway, we're going to talk about security models and evaluation methods today, and a little bit about hardware. And the rest of this stuff will be in later weeks. So security models, this is the classic CISSP material that I remember learning. These are the theoretical mathematical type models that underlie security. Computer security started practically in the 70s or 80s, and they tried to make a mathematical computer science model of what a secure system would be. And the big steps forward to the Bell-LaPadula model, the BIBA model, and then the Clark-Wilson model. And these other ones are smaller issues, but those are the 3 big ones that I learned when I first learned my CISSP maybe 8 years ago. And here's the concept. You have low clearance and high clearance. And this is all thinking in a military context for like top secret information, although in a civilian context, you use the same system. So in a military context, you have unclassified, confidential, secret, and top secret, and that's called up. And the other direction is down. And so in order to restrict it, you have a rule. And the simple rule, this is the Bell-LaPadula model. The simple property is that if you have a low security clearance, you cannot read information at a high clearance. This is obvious. This is, of course, what everyone means. If there's something marked top secret, then only people that are cleared for top secret should be allowed to read it. That part of that is to protect confidentiality. And of course, the first thing people think of in security, and the first thing they did think of in security, is keeping the secrets secret. That's confidentiality. So you could write up, you could take something from a lower classification and add it to some information at a higher classification, and that would not be a security violation. But you cannot write down. You can't take something out of the top secret bucket and put it on on just a secret machine, or that would violate security. So those are the 2 rules: no read up and no write down. And what those do, so people with top secret can read down, that's fine. And people, and information at the lower level can be written to a higher level for analysis or something. So write up is okay and read down is okay, but read up and write down are not okay. That is the first model of security. And so you can define a state model where you have states of information and where everything is, and you consider moving from one state to another, and that's the point. So this is the Bell-LaPadula model. Those are the rules: no read up and no write down. And the result of this is you have confidentiality. The secrets remain secret, but it does not maintain integrity. Since you have write up allowed, a person with low clearance could write onto the top secret data and therefore corrupt it. And this is essentially what we have now in the reign of Trump. We have him making up conspiracy theories that are completely false and then entering it in the public's record. So now I have people come to me and say they believe that it is a Chinese military that leaked out the coronavirus, because that's disinformation that came from the Russians, and all the Russians have to do is leak it to Breitbart, and they'll put it on Fox News, and Trump will believe it and amplify it. So it's the kind of thing, even though it's not a direct violation of confidentiality, it is a violation of integrity. You can have information that came from an untrusted source that moves up into the high confidence, high security level, and that's the problem with the Bell-LaPadula model, is it does not provide integrity. It only provides confidentiality. All right. So another property you might want is tranquility. This is where security labels don't change. you can, if you're going to allow them to change, then you're going to have some process for changing them. And this is a weakness of the American system. We have a lot of things marked top secret, and it's very hard for them ever to get declassified, because of course it's very hard to ever decide that you're done making them secret. And anyway, so another way to do this is a lattice-based access controls. You have subjects and objects, which are people and data. They're modeled in various ways. Clearance is vertical, need to know is horizontal, and role is also horizontal. And so you have bounds of access, and they have this system here where you have a lattice, alpha, beta, and gamma, and these complicated mixtures of properties you might have to reach certain data. This is an attempt to generalize beyond this simple vertical control of unclassified, classified, secret, and top secret. Right, but then the BIBA model was the next big one. This attempted to fix the problem of protecting the integrity of data. And it's just the opposite of the Bell LaPadula model. So read down means people at a high level cannot read data at a lower level. So they can't get untrusted data and move it up high. And no write up means you cannot take any low level data and put it up high. This is an interesting model. This protects integrity, but not confidentiality. Everybody can read up, so everybody can see all the data. And to me, this is clearly what happens in, say, the Roman Catholic Church. You have this document at the top, like the Bible, that is supposed to be perfect. Everybody can read it. Nobody can change it. That's integrity. You don't have any secrecy, but what you have is everybody stays on mission. They can all see the document. The other one with all that confidentiality, but no integrity, has the result that people often don't know what other people are doing. And there was a case I heard from the KGB where they broke into a safe in Washington and stole a document, and they didn't know that a previous KGB team had already stolen the same document. But because they have such secrecy, they didn't know what the other people were doing, and that's what you get in the Bell LaPadula model. It's so hard to access confidential data that you can't share information. So the alternative is this: you get integrity, but no confidentiality, which is appropriate if you have no secrets, but you want to make sure that everybody stays on mission. Anyway, so this introduced the more modern concept that you cannot have a perfect system. You cannot have perfect integrity and perfect confidentiality. You have to balance them. So the Clark-Wilson is the one that leads to, say, the modern world, where you have things like an Active Directory domain controller. Now subjects access objects by programs. The programs have limitations, and you have these transactions and separations of duty. Yes.
Active Directory based on.
Well, I think so. Yeah, Active Directory, it works this way, essentially. You do not have such a simple system as no read up and no write down. Instead, you have this sort people into groups, and this group has read access to this and write access to that. So you have a much more complicated situation. It's not as simple as just straight up and down. And that's what you need to match the real requirements of modern business. So there's these well-formed transactions are the only things that are allowed in the state machine. Transactions move the machine from one state to another. And there are unconstrained data items that enter the system where you don't trust these, like untrusted user input, and you convert these into constrained data items. Now they fit your security model, and you make sure that all allowed transactions preserve the security state of the model. This is essentially what group policy does, or at least what it's attempting to do. So you have a transaction procedure, and it makes these into well-formed transactions. So all the allowed transactions are ones that leave the machine in a state that obeys your security policy. That's the goal. So you define your policy to be whatever you want it to be, and then you can trust the system to make sure that nothing will violate the policy. A separation of duties is a similar issue where it takes, no one person can commit fraud, because if you do something important, another person has to also approve it before it takes effect. Neither one of them can do it all alone. So anyway, that's the three big models, and I've got some cahoots about that. And that would be, let's make this a little smaller, 125.3a is here. There we go. And let me start it, make sure it's randomizing, which it is. And all right. And we've got new music.
It used to be a 6-digit, now it's like 7-digit.
Oh yeah. I think they're getting more popular. Anyway, I got that, and I've got a place to put the answers. There. All right. Yeah, it might be Bernie time. People are freaking out now. It looks like Bernie's winning. Now they're freaking out and bringing up all this stuff in the past. We'll see how it goes.
No, Bloomberg's gonna win.
They're bringing up all this dirt from Bloomberg too. I don't know. I think Bloomberg. I think Bernie's got a better chance than Bloomberg, but we'll see. Anyway. Oh, sure. That's the problem with Bernie. Bernie supported all sorts of communist dictatorships and stuff. You know. Well, we'll see. But I agree. That's what a lot of people think, is that Bernie can't survive the criticism of all the things he said about the Sandinistas in the 70s and 80s. Yeah, well. One thing about Bernie is he's consistent. He probably hasn't backed down. Yeah, we'll see what happens.
Entirely depends on the age group you're asking.
Yes.
Certain age groups believe Bernie is not.
They do. Older people tend to not like him that much. Yeah. Anyway, we'll see what happens. I think the end result is we'll get more Trump. But anyway. So, looks like 6 is all I'm going to get. All right, let's carry on. So, all right, which one of these uses alpha, beta, gamma stuff? Okay, that's the lattice system. All right, which one has no read down? That's the BIBA model, which gives you integrity but not confidentiality. All right. And which one gives you no read up? That's the Bell model, the simple one, where low clearance people can't read high clearance secrets. That's the simple, obvious one, protecting confidentiality, which is the first thing people thought of about security until they had to broaden their view and realize there's confidentiality, integrity, and availability, and you can never have all three. All right. And which model ensures confidentiality but not integrity? Yeah, that's the Bell model. All right. So we got Bernie. Well, you'll have to tell me who that is. T. False is a real name, though. Yep. I recognize the name. And Amparo is a real name. Good. And Bernie, I'm guessing, I don't know, that might be Ed. Anyway, they'll have to come out of the closet if they want their points. But there are some people who don't seem to care about the points, so we'll see what happens. Anyway, all right, let's take a look at some more of this. So, all right, then there's information flow models where you don't consider the ends. This is how information flows, no write up and no loop down. This is the BIBA and Bell-Pudala model. Another model is the Chinese wall model. This is how you handle conflicts of interest in banks and lawyer firms, where you have two people in the same company, but they're not allowed to talk on certain topics. And this is horizontal control, like need to know and such. This is an idea that you can avoid conflicts of interest by limiting how data flows inside the company. Non-interference is the desirable property of a security system, which means that whatever happens at a high clearance level should have no effect at all on what happens at a low clearance level. And this is a desirable property. It is very difficult to achieve. One famous example, which apparently is real from I think the 80s, is that all you have to do is watch the pizza delivery in Washington, and you can tell when we're going to do a major military move. Because when they're planning to do a major military move, everybody has to stay late for briefings, and they order a bunch of pizza. And so by just observing the total amount of pizza purchased in an evening, you can tell when a major military move is happening. Anyway, that sort of thing. Another one, there's a lot of side channels, like you can deduce cryptographic keys by measuring the power consumption of the processor and that sort of thing. So even a low-level activity like the power consumption, which doesn't require any privileged access, can give you clues about a high-privilege activity like an encryption activity.
Wait,
Yeah.
if I know that, why can't I just write like another for loop running in the background to?
You can, and that is the cure. That's why people try to make constant time algorithms that will take the same amount of time for every value of the key, and they try to make other algorithms. It turns out to be extremely difficult to make an algorithm that doesn't give you any clues at all. But the simplest thing is to just waste some random amount of time. That will add some noise.
Right, like the noise distraction.
That's right. And that doesn't really fix the problem totally. It means it takes more samples to wash out the noise. But it is a permitted measure. And it turns out that the real cryptanalysts try to write things that give no clues at all. And that turns out to be almost impossible, but you can certainly make it better. And an air gap would seem to be a logical clue. Just have a totally separate piece of hardware running the high privilege stuff from the low privilege stuff. That would seem to help. But anyway, so then there's one with take, grant. You can do things like take, grant, create, and remove. And now you have a complex set of relationships. So Alice can create and remove privileges to the secrets, which she controls, and she can then grant privileges to Carol. But Bob, the supervisor, can take away Alice's privileges. And this is another way to accomplish the same thing, where you have the complexity of a real system with data custodians and data owners and administrators and stuff that all have certain rights to affect what other people can do. All right, and so you have a matrix here. This person can read and write and execute. This person can read but not write, and so on. You have all these permissions, just like a modern data access control list that you see in a Windows server. Then there's a Graham-Denning model where you have all these actions: destroy subject, create object, destroy object, and so on. And then you have rules for who can do these things to what. These are just various ways to formalize computer security. There's an HRU model as well that just sorts them into different categories. There's no simple right answer or wrong answer. This is like all those compliance frameworks. They all do approximately the same thing in different ways. Here's one I just checked today. I wonder where this came from. This came from a Department of Defense directive from 1988 that defined these modes of operation: dedicated, system high, compartmented, and multi-level. These are how you implement these things in hardware. So dedicated is the simplest one, where you have to have an air gap. Each system only has one level. You have a computer for top secret stuff, and there are people that tell me in the Department of Defense there are people with 7 computers on their desk, because you have to have an entirely separate system for top secret and classified and unclassified and so on. This is one way to do it. The simplest answer: you get air gap between each security level, and so that there's no easy way to move data from one level to the next. System high is another way where your system contains objects of mixed labels, but no person is allowed to use the system unless they are cleared up to the highest level of all the data on that system. So this is a small step from the dedicated system. And then there's compartmented, where everybody has the clearance, but they don't necessarily have formal access approval or need to know. So this enforces the vertical control, but not the horizontal control. That's done with compartments, and you have some kind of technical control to enforce need for no. And then there's multi-level, where you have one computer system and it has all these different levels and clearances on it, and you trust the computer to make the decision of who's allowed to do what. This is, like I say, the Microsoft Active Directory domain controller. All the data is on a computer system, and you trust the domain controller to control everybody's access to everything. It's all the multi-level is all on the same physical hardware, and you're trusting the reference monitor. It's part of the computer system that somehow keeps track of who everybody is and what they're allowed to do, hopefully. This, of course, is the cheapest way to do it. You don't have to pay for all those different pieces of hardware, but it would seem to be the most risky. Anyway, then you have evaluation methods. So this all came from everything. I've probably mentioned it several times in this class. Everything in security started with the military. The military obviously had the first security issues, and then the civilians imitated a sort of watered down version of it, became popular in civilian world. So TCSEC was the start of it all, the Orange Book. There was a series of colored books in the 80s for security in various environments from the Department of Defense. And so first came TCSEC, the Orange Book, and then came ITSEC, and Common Criteria were later models intended to replace TCSEC. This is the famous Orange Book from the 80s. This is part of the National Institute of Standards from the NSA, and this gave you ratings of security systems. And it works like this. D is essentially no protection at all. That's like MS-DOS and floppy disks. Physical access to the disk means you can read and write all the data on the disk. There's no permissions at all. That's no control at all. Discretionary protection is what you have with a modern laptop, like an Apple or a Windows laptop. Somebody owns it and they can decide what to do. I can share it with others or not share it with others at my discretion. Mandatory protection is where you now have a more structured thing and some kind of administrator. We have to get permission to control it. And the highest level is verified protection, where you have a closed loop of security, where you declare your security goals, you implement a policy, you measure how effectively the policy is working, and then you improve your policy to continue to chase your goals. That's the closed loop, which is the highest level of everything, where you're verified that it actually works. So then there was the Red Book, which was the network version of this for network security. And then came the European system, which was ITsec, which separated functionality and assurance. With functionality is how well it works, and assurance is how well you can evaluate that it's working. And so you have assurance correctness from E0 to E6 being the highest. And then you have a mapping between the two here. The E is the no good, and the F down here gets up to F to E6 gets you to A1. It pretty much maps across. And both of these are now considered obsolete and replaced by the International Common Criteria, which supersedes them both as a target of evaluation and a security target defining what your goal is in the world of security. And then you have a protection profile and an evaluation assurance level. And you end up with, again, a series of steps, which are pretty much the same thing. Functionally tested just means it works, then methodically tested and checked, designed and reviewed, formally verified, and formally verified, designed and tested is your highest goal. And the from one level, the big difference between these levels is how many administrators there are and how many documents there are flying around proving that you checked this and you checked that, and this has been updated and this has been reviewed. So that's why you end up being very expensive to make things at these high levels of assurance, because you have tons of bureaucracy filling out reports, just like compliance frameworks. All right, so I got another Kahoot about that, which is 3B, which is here. Okay. All right. Kind of screwy music. I guess that's supposed to be the sound from the needle swiping across the record.
Wait, Sam, do you have a RSA workshop?
No, I did it last 2 years. I didn't do it this year because last time I taught at RSA, the internet didn't work at all and the students were unhappy. So I taught one of B-sides instead.
Oh.
Yeah. All right, we got 7 people. I'll just wait a few more seconds. I think we got everybody that's coming. I guess not. Okay. Yeah, so hands-on workshops are not that common at RSA, and they never seem to get their act together. So
Mostly talks.
I guess, yeah. Yeah. The talks are pretty good, but I wasn't that motivated, so I didn't go. I just went to B-sides. But if you guys want to go, they tell me Thursday and Friday are student days. You can get in and go to a job panel and stuff. So if you do that, it's worth extra credit, but I'm not going. All right, let's see how these look. So, which mode enforces an air gap between every security level? Okay, that's dedicated. You have dedicated hardware for one security level. This is the most expensive and probably the most secure way to do it. What TC sec level does your home laptop fall under? It's a C. These are like grades you get in class. A is the best, D is the worst, and your home laptop is one step up from the bottom because it's not MS-DOS anymore. It's up to Windows or something, and that gets you to C. Which security feature prevents a covert channel? Okay, that's non-interference, which means that the high security activities do not have some effect on a low security, which could be observed and leak out the information you're trying to protect. All right, which operation mode uses a reference monitor? That's the multi-level model. And these are the official terms from the Orange Book, and they can do to computer lexicon. In the Orange Book, I think is where they had the trusted platform module. And that's why Microsoft had to define their term, trusted platform module, to create a trusted platform. These military terms ended up being the names of hardware, which were designed to meet for military specifications so they could sell them to the government. And anyway, reference monitor is the part of the operating system that enforces these permissions. And all right, what's the modern international standard for security evaluation? Common criteria is the new one. First was TCSEC in America, then ITSEC in Europe, and the common criteria is the one that's the international standard now. All right, so I got CDH, that sounds like real initials. My grader might figure it out. Vote March 3rd, I'm guessing that's probably Bernie. And Ampero, good, all right. All right, good. Hey, you get to see runners up, that's unusual. Anyway, so, all right, good. Let's take a look at the third section. That's as far as I'm planning to go today, one more of these, and then we'll do student presentations, of which we have several. So, secure design concepts. One fundamental concept is layering, where you have layers of activity like applications, the operating system, kernels, and hardware. This is abstraction is another concept where you don't present the user with details they don't care about. They see something like an email or a web page. They are not aware that there are packets and IP addresses and all that jazz happening behind the scenes. Yeah.
Is there something like below, is it ring 0?
There is now, yes, below ring.
Hardware, is that hardware?
Ring 0 is hardware, but now they consider hardware-assisted virtualization to be below that, and they call it ring -1 sometimes.
So that's hardware.
Yeah, it is, but it's letting certain software items have a direct access to the hardware.
Okay.
So it kind of is outside the model. It's a very good point. It's sort of like a similar one is VLANs, which are between layer 2 and layer 3. Every time you have a model, somebody builds hardware that breaks your model. And so I think there's even something called layer -2 now, where I forget what it is. Something beyond hardware assisted virtualization. I think it might have something to do with, there's now these special hardware security modes, like a trusted coprocessor and stuff, where there's another processor and machine doing stuff that the main processor can't see. There are things, you know, that there are things that don't.
Just TPM or trusted?
Yeah, that's the TPM and the secure element, and there's special hardware cache. Yeah, there's various other things in there that don't really fit in that model.
Okay.
Yeah. Anyway, so you got security domains. So in general, you got kernel mode. This is where you have direct access to the hardware, total control of the computer, and user mode is where you run most user programs where they do not have direct access to the hardware. They have to go through the kernel. And the idea is you can have user mode programs which have errors and crash, but they can't crash the whole system because they don't have access to the kernel. So you have the ring model. The hardware enforces this from ring 0 to ring 3, but the only rings that are used by any modern operating system are ring 0 and ring 3. The ones in between are not used. They were implemented by old systems like Minix that never really caught on. So hypervisor mode is the one called ring -1 by some people that allows some virtual machines to run in ring 0. And this is how you have craziness. Like you can have a Windows 32-bit machine and you can install VMware on it and you can run a 64-bit virtual machine on a 32-bit OS as long as the hardware is actually 64-bit. Because the virtual machine passes commands straight to the processor. It does not pass through the intervening operating system, which is kind of madness. And this is how VMware has claimed for years that their virtual machines run 100% as fast as if they were installed on the bare metal. And I don't know if that's true, but this is how that could be true. The instructions go straight to the processor. They do not pass through the intervening operating system. And that's what this hardware-assisted virtualization is intended to create. So there are open systems where everything is published and you know what's going on, like the IBM PC. And then there's closed systems, like the Mac was the big one here. Mac would have no serial numbers on the chips, everything's proprietary. You're not, and you're still doing it. You're not allowed to run the Mac operating system in a virtual machine or on different hardware. If you make a Hackintosh, it's technically a violation of the user agreement, and you can do it on an amateur level. But if you actually start selling them, then they'll actually send you a lawyer and shut you down, because it's a closed system. You don't have the right to really know what's happening in your Mac the way you do with PCs. All right. Then there's secure hardware architecture. So you got the computer case containing all the components and the motherboard, which has all the main chips and such. Then you got the bus, which moves data back and forth from the CPU to the display and other things like the RAM and the keyboard and the hard disk. The bus is the communications channel. We now have Northbridge and Southbridge. Northbridge is the high-speed bus to go between video memory, RAM, and CPU, so you can update that quickly. The slow things like keyboard and hard disk and USB go on the slower Southbridge channel, because those intrinsically slow devices don't need the fastest communication.
But I think nowadays they only have the Northbridge, right? They just have one chip.
I don't know, actually. There was a time when they had North and Southbridge. Maybe it's all Northbridge now. I don't know. You probably know more than me. I never got my A+. So I'm pretty shady on hardware, shaky on hardware. Sorry, the CPU has an arithmetic logic unit that does things like XOR and mathematics, and has a control unit that fetches instructions and lines them up to pass them to the ALU. So the process is you fetch an instruction, you decode it, you execute it, then you write the results. And those 4 steps are what happens. Most instructions take several clock cycles, so now we have pipeline, unfortunately, where it starts the next instruction before the previous one finished, which turned out to be a disaster and led to the Spectre and Meltdown leakage of information, where you have begun to do the next instruction before you have completed the previous one, which would have told you you don't have permission to do the next one. So even when you try to do something you're not allowed to do, part of that instruction does execute it within the processor, and it turns out that there is some leakage of that information. Anyway, interrupts are a request to stop the current task and do something else because something happened. And each task is broken into process is a program you launch, and each process typically has multiple threads. And this is so you can have one thread proceed while another thread is waiting for something slow, like user input. So multitasking is what all modern operating systems do. The threads are moving forward and several programs can run at once. Multiprocessing is only possible if you have multiple CPUs, which most people do these days. Multiprocessing became popular because of heat dissipation. They tried to make CPUs faster and faster, but when they got up to about 2 or 3 gigahertz, they could not get the heat out of the processor fast enough, so they could not keep increasing the speed of the processor. It would burn up. So instead, they had multiple processors, like 4 cores or 8 cores. But the problem is most people don't know how to write code that can efficiently use all those cores. So you don't really get the benefit you'd like to get. But that's, for the last 10 years, the actual clock rate has not been going up much. And it's hard to make computers a lot faster unless you can find better ways to do multiprocessing systems. All right, so there's a watchdog timer that'll reboot the system after something crashes. Cisco routers have this. Every 30 seconds, they check the heap. If anything's wrong on the heap, they just reboot the whole router. They don't have any error handling. If any kind of error happens on a Cisco router, it just reboots the whole system. All right, so complex instruction set computers are what Intel uses with many, many instructions. Reduced instruction set computers are what ARM uses. And they're also what the old Motorola Mac used, where they have a smaller number of instructions and they're hopefully optimized to run faster. So in the exploit development class, we're developing ARM exploits, and you can see that it takes more ARM instructions to do something than it does on Intel. All right, so you got direct and indirect addressing. So if you add EAX to 8, you take the immediate value 8 and add it to whatever's in EAX, taking EAX from 1 to 9. If you add bracket 8 to EAX, then it will go to address 8 and find whatever's there and add it to EAX. And if you have indirect addressing here, you add the immediate number 8 to the address EAX. So you take the contents of EAX, and that contains 12, and that tells you to go to location 12, and that's what you add. So those are direct and indirect addressing. The brackets mean that the number inside the bracket should be interpreted as an address and referring to that memory location. All right, so we talked about that. Then there's memory protection. Each process has its own memory space. You see it in the memory map in things like Ollie debug. So the idea is that they can't affect each other directly. And there's process isolation. Each process supposedly has its own virtual memory. It can't see the memory reserved to another process, and therefore they won't interfere with each other, although they have to take turns sharing the processor. And that's why if you want one process to talk to another process, you have to use special objects like mutexes, which are flags put in the operating system that can be seen by all the processes. When a processor starts, it's in real mode, which is a really old mode of processors from the old days with a small amount of RAM and no process isolation. And then during boot up, it switches to protected mode. All right. Virtual memory lets you have isolation between the processes. If the kernel tries to access memory, you get a page fault, and then it has to load that data from RAM because you ran out of memory, and that memory was swapped down to the hard drive, and the result is that slows down your machine very much. Those are called page faults. If you don't have enough RAM in your machine, you get a lot of page faults, which means your machine runs really slowly because it keeps looking for data, and that data is not in RAM. It has to swap data from the hard drive to get to it. The BIOS is code that starts when you first turn on a machine. It runs a power on self-test to see if it can find a keyboard and a display device and some RAM or a floppy or a hard drive to boot from. Then it boots from that. You can have write once, read many storage like CDR and DVDR. These are commonly recommended for things like logs that you don't want anyone to be able to erase. I don't know how many people are still doing this, but this is an old recommendation. The trusted platform module we mentioned was put there specifically in Vista and later versions of Windows to create what was called a trusted platform by, I think, the Navy, which is the thing required to meet these standards of security. And so this is a special cryptographic. The point is you have to have somewhere to put a key. If you're going to encrypt the hard drive, you have to have the key somewhere. But if the key was in RAM, you could have a virus that stole the key or malware. So you have to put the key somewhere. You have a special place to put the key, which is in a special chip, which is not anywhere in the address space.
So this is done on hardware?
Yes.
There's a separate processor.
Yeah, there's a separate processor on the motherboard.
Memory, I'm guessing.
Yeah, it's got its own.
System.
Yeah, it's got its own processor and code and stuff, and it has the keys. So you send it a signal saying, decrypt the hard drive. And you get the password, you pen the password, it tells you if it's right, decrypts the hard drive, but the processor never sees the key. So you can't steal the key. And so now Jacob Applebaum was part of the team at Northbridge that actually did steal the key. Joe Grand, I think the main guy, he actually took a TPM and dissolved it with acid and reached in with a tiny needle and found a pin and sucked the key off that way. So it's not absolutely, nothing is perfect, but he had to destroy 100 TPMs to get one to make it work once. It's difficult, if you're really Osama bin Laden, they will get that key. But the question, all you're doing is making it more expensive for the attacker. That's all any security measure does. So you have to balance your security measures against your threat modeling. How much do people want to get in?
Like risk versus like overhead.
Yeah. So I mean, if it's just my laptop, you don't think anyone's going to spend $1 million and dissolve the TPM to get in. It's probably just a student trying to cheat on their homework. So I don't really need this kind of exotic protection. Yeah.
The source sphere is kind of like that.
What's that?
A source sphere.
Source.
Azure
Sphere. Well, Azure Sphere. Well, yeah. If you can, I don't quite understand Azure Sphere. I just read a little bit about it today. I didn't really get it. But they give you hardware and software.
Wait,
yeah.
So is there like a software kind of trusted platform module?
Yes. In Android phones, quite a few of them simulate a secure element in software instead of having real hardware secure element. I think Google Pay does that. Google Pay on some phones does not actually reside in a separate chip, whereas Apple Pay always does. So I think there's a special secure mode of some processors. So yeah, some of them do simulate this, which is of course in principle less safe. So then there's data execution prevention. This means you can put permissions on RAM and specify whether RAM is executable or not. And this has been in all versions of Windows starting with Vista, and it made it much harder to do buffer overflow attacks. It stopped a whole generation of attacks. Address space layout randomization also been around in Windows since Vista. And this means every time a process launches, it randomly relocates in memory, so you don't know where you are in memory. This means all the code has to be compiled with position-independent code, which is a switch in the compiler, although it's now the default in most compilers like GCC. But anyway, these two things together ended a whole generation of buffer overflow attacks. They both made it much more difficult to write buffer overflows, which we're doing in, of course, the exploit development class. All right, and we're down to the last cahoots here. We're right on time. So 3C is here. All right. All right, here come some people. Yeah, we could vote already. I got my ballot. I could mail it in. I don't know whether I should vote for Bernie or not. I don't suppose it really matters, but anyway. All right, I'll give it a few more seconds. But I could mail in my ballot any day. I guess they still haven't counted the votes in Nevada, and I don't think they still have the final count from Iowa either. People are saying they're never going to do a caucus again. This sucks, which seems about right. Trump is making hay of this. He's saying, no, Democrats are idiots. They can't even count the votes, which unfortunately is true. Anyway, all right. Well, there was 8 a minute ago, weren't there? I'll wait a few seconds to see if one of them comes back. All right, looks like somebody jumped ship. On we go. Users can't handle the truth, so the computer lies to you. What is the dignified term for that? That's called abstraction. There you go. All right. So, a cryptographic coprocessor. That's it, the trusted platform module. All right, which CPU ring is user mode? It's ring 3. Ring 1 is not used and ring 2 is not used. There's only 0 and 3. All right. If I launch Microsoft Word, what has been created? But it's a process. Within the process are threads, but the best answer available is process. And if this seems unfair, that is quite in the spirit of the CISSP. Anyway, so, all right. So the communication channel between components. Bus is the best answer. Again, you could argue the IRQ is also meets the definition, but again, in the spirit of the CISSP, you have to choose the best answer. And it's not as simple as one being 100% right and all the others being 100% wrong. Anyway, Ampero is 1 3 times, good. True Grit. And Vu, that's a real name, good. So I got various fake names here. And if these guys don't come out of the closet, they aren't going to get points, but maybe they don't care about 3 points. Anyway, all right, so I'm going to stop the recording. And I'm going to do we'll take a 10-minute break, and 5 after 7, we'll do the student presentations.